Hello and welcome back to the QuadTree project. So in the last episode, we finally were able to get dynamic updates of the QuadTree. So this means that, as you see in this animation, as the points start to move outwards, they start to fill the capacity of the outer leaf nodes of the QuadTree, and so those start to subdivide. So essentially, we're allowing the QuadTree to understand how the points are moving and to dynamically update based on when the points move out of a leaf node or into a leaf node. So based on this, we should actually be able to dynamically update our QuadTree and dynamically calculate interactions between particles, and also query the QuadTree for all of the particles within a region of interest. So this is useful mainly in particle simulations where you're trying to find interactions between particles. So for example, if there's a particle in the center and you're calculating the force on that particle from all the other particles, usually these forces are usually distance-based, so a particle that's really far away might not contribute as strongly to the force as a particle that's nearby. So you would choose that particle in the center, query a radius around it, and fetch all of the particles within that radius. And the QuadTree structure makes it really, really useful to do that because you can skip doing a bunch of checks on leaf nodes that are really far away from the region of interest. So today we're going to implement that. We're going to implement the query where essentially if you define a region of interest, you should be able to fetch all of the particles within that region. So let's go ahead and get started. So here we started out with 10,000 particles. We essentially initialized them with a Gaussian distribution in position. So in the bounds between 0 to 25, it's starting at the center with a distribution with a standard deviation of 1. And we're allowing the velocity to be in any direction uniformly. So that's why it spreads uniformly outwards from the center. So what we want to do is, if I just pull up the QuadTree again, what we want to do is if I move my mouse around, and if I have essentially a bounding box around it, I want to see how many particles, or get a list of all of the particles that are within that bound. So let's build that query box first. So in that case, what we want to do is let's define a new bounds. Let's call this query bounds. And for now, let's leave it enter. Let's leave it empty. Let me just check to see what the... I think that probably just resets it to a value of 0. So if I do this, it just resets it to a value of 0, which is fine. I don't actually need that. Oh, I see. So that's based on a previous initialization. Okay, so we want to set an initial parameter. Yeah, let's do that. So let's create... Yeah, let's just do 0, 0, 0, 0. Which means that essentially we're not allowing this query bounds is very, very small, so we don't actually need it. And let's define a constant value, which is the a query radius or query distance. And let's set this to maybe 0.5. We're setting this in our world space, so it's not in pixel space, which is, as you remember, it was 600 by 600 is the size of our window. But the actual domain, so the world space, is between 0 to 25. So here we're defining the query distance to 0.5, which means we want to look for points that are within this radius of 0.5 from the center. And we're going to define the center, which is this query bounds, right? We're going to define the center as based on our mouse position. So what we're going to do is, if the event type is mouse moved, right? What we want to do is to get the mouse position, like so. And we want to convert this mouse position into our world space, our 0 to 25 space, and then set the center of our bounds to be the mouse position, or of our query bounds to be the mouse position. Okay, so this means that first thing we want to do is convert to mouse position in world space. So this is going to be our transform to world space, and that's just going to be our mouse position, like so. And so this is going to be the center. So probably the best way to do this, let's see. So probably the best way to do this is to actually do, so I don't want to have to set all of these parameters at once. So let's create an update function. And this is going to be our, and then this is going to be our query distance by query distance. So the parameters I'm thinking here, let's define this function here. Our update function is going to be our, oh, these are double, okay. Our center values, so x center, y center, and then our width values. And that should update all of these parameters here, like so. So let's do that. So x min is just going to be x center. So am I defining the width or the half width? I think this should be the half width and then the half height. So if you imagine a box of size, we don't want this to be a box of size 0.5 by 0.5. We want this to be a box of 1 by 1 that is centered at this mouse position. So the distance from the center to each edge is going to be 0.5. If that becomes too confusing, we can probably change it later. But for now, let's keep that as the standard. So xmin is just going to be the center minus this, and then xmax is just going to be center plus the half width, right? And we'll do the same thing for y, like so. And I don't think I need to set anything else. Oh, I need to set the width and the height. So the width is just going to be 2 times half width. And then the height is just going to be 2 times the half height, like so. Great. So now we're able to update our bounds. So let's see if this works. Let's start to render our query bounds. We need a new render function for that. So let's go to render.cpp, or actually we need to define it here. So, and this is just going to be a const, and then the render window, like so. Okay, and let's define this in our render.cpp. I'll just put it up here because it's going to be a small function. Render bounds, and this is going to be const. And I think it's fine to keep this really simple. So this is just going to be our rectangle. It's fine if we're only drawing one of these bounds at a time. So really, we don't need to really complicate our life with trying to create vectors and all of the optimization that we did with rendering QuadTrees. So this is just going to be an SF rectangle shape, and I think this is, oh, this is the size of the rectangle. Okay, so this is going to be bounds dot width and then the bounds dot height. So okay, so these are all, I mean, I should update it so that all of the doubles are floats. Because we've been using float for everything. I don't think this is going to cause a problem. And this should also be float. Let's just change all of the doubles to floats over here as well. Okay, so that's fixed here. We can come back and see if we need to fix things later on. And then we need to set the position of this. So the rectangle dot set position is going to be the bounds dot x min, and then the bounds dot y. So remember that for SFML, the position is set to one of the edges, or really the top left edge, because in computer vision, your origin 00 is going to be the top left of the screen. And we already have this calculated, so we can just set the rectangle there, and then the rectangle dot set outline color is just going to be our, let's just call it maybe, we want to differentiate this from everything else, so let's call it maybe red, because we want to query points, and then we want to set the outline thickness, and let's make this smaller than everything else. Let's do a value of 1. I don't remember what I did here. I think I should set that over here, but for now this is fine. I don't remember what I said for the thickness of these lines. I think they might be just 1. Maybe I can make them 2 pixels wide. So let's see if this works. Okay, it ran without an issue, but we're not seeing, oh, because I didn't call the render bounds function. So let's render the bounds. No, we don't want that. So render bounds, and this is just going to be our query bounds, and then our window, or sorry, that. Excellent. Okay, let's render this. No problems again. We're still not seeing the bounds. Did I forget to update the query bounds? Let's print out both the pixel space and the world space. Right, so this is mouse position.x and mouse position.y, then mouse pause world.x, and then mouse pause world.y. See if what these values are. We should remove the frame counter actually. That seems to be correct. I need to remove the frame counter. Oh, I see. So some of these values are actually negative, which is not true. But that might be because I was moving the mouse off the screen. So this is 0, 0, right? And that should be 0-ish, and then all the way down here, 600 by 625. Yeah, that's correct. So this is all correct, and I'm just not sure why it's not being updated. Okay, so this is correct. So instead of this, let's say query bounds, query bound center, and this is going to be our query bounds dot. Maybe I should call it x min and y min instead. Edge. Yeah, that seems to be correct. So there's something wrong with actually rendering. Did I draw window draw? I forgot to call a window draw. So window draw rectangle. That should fix it. Let's remove this print statement just so things are a little clean. Use you, yeah, because we're not. Oh, there it is. Yeah, that makes sense. But we forgot to convert it back to world space, so we just need to do that. That's easy enough to do. Bounds, no, render.cpp. So we need to transform to world space of that. No, sorry, transform to pixel space. So we also need to transform this to pixel space. I forget if we had a. We just need to multiply by the scale, I think. Double to float. I think that's probably because we set our, yeah, okay. These should also be float. That shouldn't, I don't know if, yeah, okay. So that was a good catch. This should also be a float because these were extern functions. That's a const. Okay, great. And now, there we go. So we should set the fill value to be none, but as we move the mouse around, we're able to see where the query box is. So essentially, we want to move this around, and we want to see all of the boxes inside it, all of the points that are inside this box. You can even make the box a little bit bigger, but that's for later. I need to just check to see how I do. I don't know if I can do a null. That's not right. So let's check. So back to the SFML library, we have our set fill color. Oh, SF color transparent. And if we do that, it should make it transparent. Great. So there's actually a specific function for that. That's fantastic. So we just do SF color transparent. Okay, let's see if this works. There we go. Now we're able to actually see through the box. And as we move this around, we should be able to query. I lost the counter. It looks like it's a little slow in rendering this, but we'll see how it goes. I think I should be able to limit the frame rate of SFML's window. So let's see. This is back to the SFML docs. So the SFML window. Oh, no, that's not what we want. Let's see how to make my window transparent. So set frame rate limit is what we want, but I do want the actual. So I want I want the actual this is not the FAQ. I want the documentation. So I want the window class here, or it was the render window, right? The render window, and then this should be set frame rate limit. So I should be able to just call the set frame rate limit up here. Let's try that out. It just takes in, oh, where did I go? It just said takes in an unsigned integer. Okay, let's try that out. This should be in QuadTree.cpp. So down here, I should just say set frame rate limit, and let's just set this to 120, which is double of what we're actually doing at 60 FPS, but that should be good. It's a little bit smoother, not too much, but that's fine. Cool. Okay, so now we have our query. What we need to do is essentially what we want to try and do is we want to say from our quad tree, we want to query based on our query bounds, like so. So we pass in a bounds object, and we should be able to get a list of particles. I don't know if we want to have the query return the particles, or if we want to have it have basically pass in a fresh set of particles, like an empty vector, and then it fills the particles. We'll see how it goes. So all of this should go into, let's remove interactions, render, we'll keep bounds. So that should go into QuadTree.h, and what we want to do is, after update points, for now, let's do a void function, and then we'll figure out what the function signature actually looks like. So this, we want to pass in a query bounds. Let's just call this explicitly query bounds. And so what this is going to do, let's just walk through the algorithm really quickly. is it's going to first step is going to check if the bounds intersects the current bounds, right? So let me just render this out. So here's our quad tree. Let me remove the points for a second. So here's our quad tree. And basically, we need to check whether the red box is overlapping with any of the existing box. So if it's over here, none of the other quad tree, all of this should not be triggered because my query is up here. So I should only search for particles within this box. If I'm here, it should search against these four boxes. So this one, this one, this one, this one. So it should search with respect to those four boxes. And if I'm here, it should search within all of the small subdivided boxes here. So the first step is to actually check whether our query box is contained or overlaps with any of these other boxes. And that should be simple enough to do. So what we really want to do is, if you look at let's handle the simple case for now. So what we want to do is, if our box is bigger than the query box, it just is saying that the left edge of the red box is bigger than the left edge of the um, the QuadTree node. And same thing is true for the bottom edge, for the top edge, and the right edge, right? So all of these are contained. The more complicated one is when you are actually, so for example, over here. So on the top left box, your left edge of the red box is actually less than your left edge of the QuadTree box, but your right edge of the query box is less than the right edge of the QuadTree box. So that means that we're actually overlapping. And the opposite is true of the top left box over here, where the left edge is greater for the query box, but the right edge is less for the query box. So we need a unified way of actually like going through all of these different scenarios. So since there's so many different conditions for overlap, it could be completely contained within the box. It could be at the corner between multiple boxes. The query box could be bigger than the leaf node, or it could be smaller. So there's a bunch of different conditions. So it's actually easier in this case to actually calculate boxes which don't overlap and then negate that condition. So basically what we can do is, for a given query box, we can look for a condition that makes us that tells us whether that box doesn't overlap with a QuadTree, with any QuadTree nodes. And then if we know that it doesn't, we'll just negate that condition, which means that if there is an overlap, that condition, does the box not overlap with our query bounds, will return a negative value, which means the negative of that will be a positive. Okay, so for what we want to do essentially is to derive a condition where this query box, the red one, does not overlap with the QuadTree. And let's see how that works. So if I move, for example, from the left to the right, we're moving our query from in the positive x direction, right? So initially, these two boxes, or maybe let me put it in the center. So this box is overlapping with the query bound. But as I move the left edge after the right node, it stops being contained. So one of our first condition is to say that if the left edge of our query bound is greater than the right edge of our target, then it doesn't overlap. That means that the entirety of that box is outside of the target that we're looking at. At the same time, you'll see that if you look at this box, for example, initially there's no overlap, but as soon as the right edge moves into the left edge of the right edge of the query box, the red box moves into the left edge of the white box, we begin overlap, right? So there are two conditions here. So either the left edge of the query box is greater than the right edge of our target box, or the right edge of our query box is less than the left edge of our target box, then there is no overlap. This is in the x direction, but we can also do this in the y direction, right? So essentially, as we sweep across, we're initially fulfilling the condition where the left edge of our query box is less than the right edge of this box. And as we move across, it's no longer overlapping. And then as we do the same thing for the smaller box, it does the same thing, so on and so forth. So let's build that condition first, and let's figure out which of the QuadTrees are contained within the query box or not contained within the query box. Okay, so what we want to do is to actually build a bounds container. So what we want to do is let's maybe create an intersects function. So this is going to take another bounds variable, and what we're going to do is our bool for not intersecting. Let's write this out explicitly, and then we can come back. Is that either the other dot xmin is greater than this dot xmin, right? Or the other dot x max is less than this dot x max, right? Let me just build the QuadTree again. And so this is what this is saying. So the other is our query bound, right? It's our red box over here. And so if the query box's xmin is greater than, is greater than this dot x max, and the query box dot x max is less than, so let's go to the first condition first. The query box's x min, which is the left edge of the red box, is greater than the right edge of the target box, or the right edge of the query box, other.x max, is less than the target left edge, right? So in this case, we are overlapping with this. In this case, we're overlapping with this. But in this case, we're not overlapping with the second box over here. And in this case, we're not overlapping with the first box over here. Great. So this is in the y x direction, but we can also repeat this for the y direction, right? So other dot y min is greater than this y max. You don't have to write this theoretically, but we're just doing it for verbosity. So other dot x y max is less than this dot y min, right? And if you do this, what we're returning is just not intersection. If we do this, then that means that there's no interaction, which means that if there's not no interaction, then it means that there is an interaction. Or there is intersection, sorry, not interaction. Okay, so this means that we can compare any bound with any other bound, right? So just to show you what this looks like, what we're going to do is to try and render the QuadTree. Let's do a clone of this for now, and then we want to render the QuadTree with a query. So let's pass in a like so. This needs to also go into the render.h. So we'll just duplicate this. And so what we will do is, as we are okay, so what we need to do, I think QuadTree lines should take in, let's just check this really quickly. So if I go back in here, I think this was vertex, right? No, I keep doing the wrong search. Vertex array. Our vertex array is going to be, I think that's correct, because yeah, we are taking a vertex array. Position. And I think our vertex is just going to be, yeah, it takes in the position and the color. So what we really need to do is to just create a, change the color of this. So let's do this. Line color, and let's just set this to a default of white. Let me just hide this. Like so. And so what we want to do is here we pass in the position. Let's do it this way. Oh, what's the easiest way to do this? Do this, 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 this. And then back here, we want to pass in the line color, like so. line color. Just repeat that. Oh, over here. Might just be able to, yeah, there you go. That works actually. Just move to my diagnostic. Like so. And so what we want to do is if qt, remember we're doing this recursively. So if the quadtree is divided, we're rendering the leaf node as a separate quadtree. And each of these quadtrees has a bounds, which we can check if it intersects with our query bounds, like so. If it does, then the line color is going to be, let's set it to maybe green instead. And we shouldn't do render quadtree, we should render quadtree with query, and this also takes in the query bounds parameter. Like so. Great. Nothing should change except in here. Oh, we don't need this anymore. Let me just comment this out for a second. Render to create another one for that, but with query, and this is going to take in the query bounds. Like so. I don't think we missed anything, so let's just render this out. So there you go. Oh, I'd see. It's actually. Let me turn off the points. So it is working, but for some reason it's not doing the very last point. Did I forget something in doing that last point? Line color. No, that's correct. Oh, I see. I think it's overwriting the last point based on. No, that should be correct. Let me render it again. Let's see what's happening. Yeah, I think what's happening is it's actually rendering this white line over this line. So it's rendering the white line of the next quadtree over the white line of this one. But for the most part, it's working. So as I zoom in here, you can see that it's actually working. Let's make the query size a little bigger. So let's set this to maybe 4. So this is an 8 by 8 wide query bounds, right? So let's render this out, and there you go. We're actually, let me remove the points. So as you see, as we hover over the different quadtrees, we're actually getting only the quadtrees that overlap, and you can see that very cleanly as we go further down here. It's only capturing all of the quadtree leaf nodes that are subdivided. So even though there's a big quadtree here that's not divided, it is only capturing all of the smaller subdivisions that are within the query bound. So this is a really neat way of querying which particles we want to identify. Okay, so what we want to do now is for all of these quadtrees that are identified, we want to query whether a particle in that quadtree, in that leaf node, is within the query bounds, right? So let's work on that. So now we know that we have a way to actually render. Our first step is done. We checked whether the bounds intersects with the current bounds, and if it does, we want to iterate over the points within the quadtree and fetch all which are contained in the bounds within query bounds. Like so, right? So our first step is done. So let's check. We now need to implement number 2. So let's actually do number 1. So this is, oh, come on. Remember, we need to do this iteratively. So the first step is to actually check if this is, if this bounds dot intersects with our query bounds. And remember that, or maybe let's do the opposite. If it doesn't, we're going to return. We don't need to do any more calculation. And remember, if I pull this back up, if a quadtree node, even though it's subdivided, let me remove the points. If a quadtree node is subdivided, if the parent node contains or intersects with the query bound, if a child node intersects, then by default the parent node will already intersect. So we don't have to duplicate this twice for the child node and the parent node. Basically, if the parent node does not intersect at all with the bounds, with the query bounds, then none of the children will intersect, right? So we know that for a fact, but the opposite is not true. So if a child node doesn't intersect, the parent node may or may not intersect. So that you can see that, for example, very close to the center where there are parent nodes which are intersecting. So there's the big green box across here, which contains all of these children down here, right? So some of the child nodes intersect, but some of them do not. But the parent node definitely intersects. So we know that if this bound doesn't intersect with anybody, then we can just move on. But at the end, we want to check if is divided. Then we want to do I think I should be able to do something like this and then leave query bounds. Yeah, that should work. So even though our leaves are unique pointers, if I do this, if I pass them by object, it should work. Great. So now we know that we're checking if the query, if the leaf node intersects with the query bounds. If it does, we need to iterate over the points, which do. And if it doesn't, then sorry, actually no. This is actually the right order of operations. So we'll move this down here. And the reason for that is if it intersects, and if the quad tree is divided, then we need to iterate over we need to recursively iterate over the leaf nodes. And remember that the parent nodes do not contain the particles. So if I go back up here to subdivide, right? So if we make the unique children, if we make the four children leaf nodes, then we're moving all of the points to those subtrees. So the parent tree actually does not contain any of these points. So if we going back to the query function. So if the bounds intersect, then we know that at least one of the child nodes is intersecting, right? It has to be at least one of them. And so we loop over those leaf nodes and we query this again. And we keep doing that recursively until we're at the final leaf stage of these nodes. So if the bounds intersects, and then 2 or really 1.5, if the tree is divided, then recursively access the leaf nodes. And this will continue to happen as long as the leaf nodes are queried. And then finally, if the tree is not divided, we don't really need an else statement here because it's just going to do the next loop. We could return here if it's divided, but again, it's just going to loop over no points, so that doesn't really matter. So for all the point in points, right, here we know that we've gone through the state where we've gone recursively when we've accessed the lowest the lowest part of the tree, so basically the leaf nodes, which actually contain the points. And here we want to check if the query bounds contains the point. And I think this is this argument to member function contains a style constant. Interesting. I think this is probably because I need to get this strange error. I think this is probably because there contains function here as well. Did I mess something up? For some reason, and I'm not sure I understand why, um, this seems to be somehow updating the bounds variable, which doesn't make sense. I don't know if this is going to help it. This argument member function contains, but bounds 35. Yeah, that's here. Um, I don't think this is a const expression either. This is strange, actually. So this is taking a shared vector of points. Do I need pass this by? It might be that I'm setting the const in the wrong place. That fixed it. Yeah, that fixed it. Oh, it doesn't fix it. Yeah, maybe I just need to do. There you go. That works. So I just need to define the const at the end. I completely forgot about that. So now we're able to get whether our query bonds.contains that point, and if it does, it actually is easier to just take in a vector of query points. So let's do a shared pointer of point, and then this is going to be. Oh, I don't need this. Let's call this query points. So I'm forgetting an extra close parentheses. This also takes in query points. So in theory, we should test if, yeah, let's do that here. If level equals 0, let's clear all of the points. Ideally, we should do that outside. And then if the query bound contains the points, then we're just going to we're going to push this point to the end, like so, right? So ideally, you could have had this where it's returning a point and then you're collecting them at each level and then you send it back, but it's too much effort at this stage. So instead, let's pass in a vector and we'll build that vector as we iterate through each level, and then we'll send it back. So in this case, we're actually updating a single vector, and so we're not dealing with merging vectors and all of that stuff. So what we should do is up here, we should create a, just the same way as this, we should actually create a query points vector, like so. And remember that this only works because our point is a shared pointer. Our vector contains shared pointers. So even if we clear out this, those points are contained in two places. One is the quad tree itself, and the second is up here in our vector of points. So it shouldn't actually be, the points themselves are not removed from memory, but it's just removed from this specific vector. Okay, so what we should do here is we don't need a return value. We just need to pass in our query points like so. Great. So now that we have this, let's just render our query points for now. Let's see if that works. Let's turn off. Okay, that's not working for some reason. So it's getting the right quad trees, but it's not getting the right points. Is that maybe because, let's just remove this. We're passing in shared vector points. Okay, that's all great. So let's just keep this as it is. So in our query, let's just print this out. Point at is inside query bounds. Let's just do the X and the Y, like so. And this is going to be point X, point Y, and then this is going to be query bounds dot X min, query bounds dot Y min, query bounds X max, and then the query bounds dot Y max. Like so. So let's just print this out every time we do hit a particle. Let's remove our particle, or reduce our particle count to like D. But we're not getting multiple interactions each time. Actually, it might help. No, let's just keep it as it is. Okay, so we are getting some up here. We're not seeing any particles. Down here, we are seeing some particles. Uh, let's see. So that seems to be correct, but for some reason, we're not actually seeing the actual points that we're entering. So that's strange. Let's see what our length of points are. Printf. Size type. I think I can just do LD. Yeah, that should work. Okay, number of query points is 0. Oh, it's still setting 0. So we're still seeing a lot of points, but it's being sent to 0, and I'm not sure why. Let's see here. So we might maybe the issue is that we're passing in this vector by instance, so we should be passing it by reference instead. So it should definitely be adding this point. So I think that the issue is that this is being we're somehow losing those points as we go. So let's maybe remove this for a second and let's print it out here and let's see if maybe we're losing our oh, I forgot to. So we are getting points inside the QuadTree. Got to print a new line. Let's do a tab here. So here, as we are adding more points, we are seeing that as we go down to deeper levels, we're getting more points. But for some reason, it's actually not being returned correctly. So why is that? Should we pass this in by reference? That's probably what we need to do. That's probably the silly mistake that I'm currently doing. There we go. Yeah, that was exactly it. So it's passing in by instance rather than reference. And so now you see that it's working perfectly well. Oh, not quite perfectly because we should not be. That's very strange. It worked sometimes and it didn't work other times. Yeah, there you go. So there is an issue where I think if you move it too slowly. Oh, that's very strange. Sometimes it seems to be... Okay, let's actually remove this. Let's try that again. That works. No, the points are definitely still remaining. So maybe the clear isn't being applied correctly. Okay, let's do this. Let's make sure that no matter what we do, we're actually clearing the query points at each stage. Like so. And we'll make it the responsibility of the calling function. Oh, that didn't actually help. Not sure why that is the case. So we want to just render the query points, right? It calls it before window dot. Okay, so it calls the window dot clear. Am I understanding correctly that? Oh, I didn't want to open that. Maybe the clear function traces all the elements on the pointed to memory is not touched in any way. Managing the pointer is the user's responsibility. Great. That is actually what we wanted. We just want to zero out this array. Maybe it's a problem with the rendering instead, actually. So this should loop over. Okay, this actually might be the issue might actually be here rather than there. So we should first clear this out. So we might be fetching the right points, but we're just not rendering them correctly. Yeah, I think that was the issue. So it was not our issue with the query; it was the issue with the rendering. So there you go. That works much cleaner. And as we query these points, we're actually generating the right points. Okay, so let's go back here. Let's increase the number of points that we have and test if this works, and also profile it to make sure that we're still getting good performance. Let's decrease the size of this query to 1, so it's a 2x2 window. And let's see if this works. I'm going to turn off the tree. And there we go. We should only see the points within this window, like so. Perfect. I can turn off the points and turn on the tree, and you see that the query bounds for the tree is working perfectly. And having both on, you see that it's actually only fetching the points within that tree. So let's test the performance of this. So the rendering should be really fast because we're only rendering a few points, right? So when I move the mouse, the rendering is taking on the order of like 10 seconds or so. When I go to a large number of points, it's taking on the order of 15 seconds. But the actual querying of the points is not really affecting things. So just to show you that that's true, let's actually render all of the points so that we don't have any differences in the number of frames per iteration. And so you see it's taking 20 seconds, and as I move the mouse around, as I query more and more points, it's not actually changing the frame time. The frame time is still locked to 20 seconds or so. So that's great. We actually have a way to query which points are within a given radius. And remember that this doesn't actually, we're creating this query bounds over here. But as long as we pass in any bounds to this function, to the QuadTree function, we should be able to get back a set number of points. So in our interactions for .cpp, we can create a force function where for each of these particles, we query the points in a radius or a neighborhood around that point. And then we only use those points to calculate the force. But for right now, let me just pull this back up. Let me just show the query. Nope, that's not what I want. Let's plot the query points. Actually, maybe before we go, it would be best to... Let's just update this function. And let's plot both the points and the query points. And then we'll pass in a color for these points. So we're double rendering these points. We're rendering the points and the query points again. That's fine. So here in render.cpp, we'll take in, or sorry, we also need the render.h. So here, render points will pass in a color. This should be const actually. And then in render.cpp, we're taking in our color. So const like so. And then instead of SF color white, we are doing, we're doing our new color. So, one more. Great. So this means that here we'll pass in white for the points that are not queried, and then we'll pass in green for the points that are queried. And I'm going to make the size of these points a little smaller. So I think I did 0.1. Let's do 0.05. So I think I can get away with 6. So just it's a little bit faster. Okay, and so if I hover over the points over here, you see that the points that I'm actually querying within the bounds are turning green, and then the points that are outside of my red square, they're staying white. So in this way, I'm actually able to really quickly query which points are the ones that I need and which points are the ones that I don't need. And this is really important for doing particle simulations, because if I want to calculate, if this is the region of interest that I'm interested in, rather than doing particle comparisons against every single particle, I just have to compare one particle against the stuff, all of the particles inside this red square. So that drastically reduces the number of particles that I have to compare with. So in this case, it's actually really, really quick to traverse, and you can still do this as the particles move. So as they move around, because we're doing this dynamically in a loop, we're actually able to see that as the particles move around, we're able to even still really quickly query which particles are of interest. So this more or less sets up our ability to do n-body simulations. A lot of the plots that we're doing right now are just diagnostic, and we haven't really gotten into running these simulations with any sort of physics or doing any sort of particle-particle interactions. So that'll come as the next step. Now we know that the QuadTree is working, that we know that the performance is really fast, and we're able to query particles based on their position. Let me just turn off the tree so you can see what this looks like. We're able to do this query. This essentially completes our the QuadTree functionality, and now we move on into actually n-body simulations. So stay tuned for that, and thanks for watching.